Student. Now I'd like to introduce one of my students who's speaking today, Alee Monaco. She'll be speaking on an overview of styrene migration from polystyrene containers into microwave food.
All right, so as we just said, I'm going to cover styrene migration from polystyrene containers into your microwave foods. And we're going to go over a little bit of the process in which polystyrene is actually formed, kind of a history of polystyrene itself, and then get into the health effects and such of migration. So polystyrene was actually accidentally discovered in 1839 by a German apothecary who had distilled an oily substance from the Turkish sweet gum tree. He thought it was a monomer at the time, and it wasn't until 1922 that another German scientist, Hermann Staudinger, recognized that it was a thermoplastic. He recognized that these properties were actually really useful, so by 1930, it was being widely used as a thermoplastic in Germany, and by 1939, it had moved to the US, and now it is actually one of the most commonly used plastics in the world. So polystyrene is a polymer of styrene molecules, and styrene is a hydrocarbon. It's basically a yellow, oily liquid at room temperature. And it's insoluble in water because it's hydrophobic, as is any hydrocarbon. It's composed of kind of two different parts. You have a benzene ring. I thought I would have a laser pointer. This is a benzene ring here, and then you have a dehydrogenated ethylene. It's formed by free radical polymerization, and what that means is it starts with a free radical, which has a missing electron from its octet. That makes it highly reactive, and it wants to form bonds with any molecule that it can to fill that octet. So the free radical is placed in a bunch of styrene monomers, and it binds with the carbon-carbon double bond that's here, which satisfies the octet of the free radical, but still leaves the styrene monomer having a missing electron on the carbon-carbon double bond here. So that wants to satisfy its octet, and thus it self-propagates a long chain of styrene monomers, making polystyrene. There are a couple of kinds of free radical polymerization that can be done as well to form kind of different forms of the polymer. Polystyrene utilizes bulk polymerization and suspension polymerization for different purposes. So bulk polymerization is the simplest form. In simple terms, it doesn't use any solutions or extra molecules to help the process. It's just allowing it to self-propagate. This results in various chains that have different lengths and masses. It's kind of an uncontrollable reaction. So it's used for very general purposes of polystyrene, but it's not very specific. Suspension polystyrene, on the other hand, it utilizes an aqueous solution and water-soluble solvents to initiate the reaction and also to maintain very specific lengths of the polystyrene molecules so that they're kind of the same mass, the same lengths, easier to control. And it ends up being these tiny little beads that are rigid polystyrene beads, and they can actually be infused with hexane gas to provide these larger gas-filled insulating balls, so to speak, of polystyrene. So in the process of polymerization, you can end up with kind of monomers that are stuck in between all the polymer chains, and that's because they weren't oriented in the correct way. They just weren't able to attach. So those are called residual monomers. You can also end up with oligomers, which are short polymer chains of 10 or so monomers. And those can also occur from depolymerization, which is when the polymer breaks apart at certain points. And those will be important when we discuss migration. So polystyrene can have various forms. The rigid form and the foamed form are both widely used. Rigid includes general purpose, which is just polystyrene at room temperature. And that is this cup on the left here that is similar to like a red Solo cup. So it's stiff, but it's still somewhat flexible. You have high impact polystyrene as well, which is in the middle, and it's still stiff, but it's very brittle, and you can't really flex it too much without it breaking. So that would be like cutlery, like disposable cutlery. Pretty hard. Then you have foamed, and the foamed form has two kinds. You have expanded and extruded, and both of those are widely attributed as styrofoam, but that's actually incorrect. Extruded polystyrene is what we know as styrofoam, and that is actually a trademark term from Dow Chemical Company that is used specifically for insulation and like packaging for materials. So ultimately, it's a different process by which you make the foam form. The expanded form is the cup that you see on the right. That's like a typical coffee cup. That's our styrofoam coffee cup. And that's expanded polystyrene. It's not actually styrofoam. If you can see in this diagram here, on the left we have extruded polystyrene, and this is the one that's true styrofoam. All of these little beads from suspension polymerization are really closely compacted, so it's an incredible insulator, and it's a little bit more long-term use. The expanded polystyrene is more permeable. You have spaces in between each of these, I guess, clusters of beads. So that's why you don't really keep a disposable coffee cup for several days. It's not something you can keep long-term because it is more permeable and will degenerate. So polystyrene is used across several industries, including electronics, medicine, construction. Its main one, though, is food packaging. It accounts for 37% of its production, and it's actually the most widely used plastic when it comes to food packaging. So you'll find that in various packaging, such as yogurt containers, takeout containers, egg cartons. It's really widespread. So with it being such a widely used food material, begs the question, is it safe? So there's actually been quite a few studies on the migration of polystyrene. And as it turns out, it does occur very frequently. The way this occurs is you have the residual monomers and oligomers that I spoke of, and they're kind of floating around in your polystyrene container. And if you recall diffusion from your chemistry class a while ago, diffusion is when you have a concentration that's really high of a substance. That substance wants to move to a concentration that's lower. So when you have a container full of these styrene monomers and oligomers, and you put it next to food, which doesn't have any styrene at all, it wants to move there. So the diffusion process basically is what initiates the migration. And then once it gets in contact with the food and plastic interface, it'll be desorbed. It'll be released from the plastic and absorbed by the food. So that is the entire process of migration. And there's several factors that can affect the amount that migrates. The largest one is going to be the fat content of your food. So as I said previously, it's a hydrocarbon. Styrene is a hydrocarbon. So it's hydrophobic, and it won't be attracted to water in any way. So studies that did testing amongst different food solvents, any of them that had high aqueous contents either didn't migrate as much or didn't migrate at all. Pure water never had any migration occur. When you have contents such as, a lot of them used olive oil, milk, things with higher fat contents, there was a lot more migration. Temperature is another major factor. It's related to kind of basic chemical principles, such as the movement of molecules. Obviously, the higher temperature, the quicker things are going to diffuse because they're able to move faster. You also have a relationship to solubility. So, for instance, I tried to do an experiment in which I used olive oil and microwaved it in a high-impact polystyrene container, and it dissolved the whole cup because it was too soluble. However, I used milk, got it to the same temperature, and it did not dissolve because the fat content in the olive oil was a lot higher, and it was able to dissolve at a sufficient temperature, whereas the milk was not. The time in which the food is in contact with the container is also pretty relevant, but for simple reasons. Obviously, the longer something is in contact with it, the more time it is allotted to diffuse, to be desorbed and absorbed. It's a pretty straightforward mechanism. The issue I wanted to address was whether the type of polystyrene affected how much migrated. And there's been several studies that showed differences between, foamed polystyrene and rigid polystyrene. However, most of the studies showed very different results. One study would show that foam did more, and one study showed that rigid did more. So I actually tried to do my own experiment, and I used general purpose polystyrene and expanded polystyrene. Ultimately, the equipment I was using, I tried using in NMR, nuclear magnetic resonance spectrometry, and that it wasn't sensitive enough, so I wasn't able to show any evidence. But I did get tiny little peaks where styrene would have shown up. It was a little bit too difficult to evaluate whether it was signal or noise, so I didn't end up writing up on that. But it's interesting to see whether there's a difference between the types of polystyrene and how much migrates. So obviously this is only important if there are health effects. There have been several studies in relation to the inhalation of styrene, and that's mostly in plastic factory workers. People who worked in factories with polystyrene ended up showing signs of lung and neurological damage, mostly related to motor skills. But there really isn't a lot of information on the ingestion. There have been some studies on animals, but not a lot on humans, so it's a little bit tough. But a couple of agencies have suggested that it's a possible carcinogen. And there was one study in Spain in which a small population, their water was contaminated with high amounts of styrene. So they ran some, tests on them to see clinically what was going on. All of them exhibited some amount of irritation to the eyes, the nose, the throat, but there weren't any long-term effects that they noted. This study was done in 2003, and I didn't find any follow-up study suggesting that they had looked at the long-term effects. So at this point, it's really unsure whether there was some sort of long-term maleffect. One study I was somewhat interested in was one that suggested that it formed protein adducts in mice. And a protein adduct is kind of a monomer that would attach to a protein and inhibit its function. So that could be, not being able to bind to other things it needed. I know in this particular study, it affected hemoglobin. So what I gathered from that is that perhaps there are protein adducts forming in our bodies, but they either aren't, there isn't enough of it to see it or not enough to make an effect. Virtually the lack of studies showing that there's maleffect in humans could be that we're not being specific enough in what we're looking for. We would need to look at certain, molecular processes. But overall, there isn't really any data to show now that there is a maleffect from styrene migration. So, as we discussed, polystyrene can take on many forms. Those forms may or may not impact how much migrates, but the migration definitely occurs. It's just a matter of whether or not that is significant to us and if it is actually harmful. So, any questions? Yeah, I'll have you in the first. Do you mean, oh, I understand. The microwaving process actually isn't particularly important. It's the heating process in general. It's merely that people don't typically take a styrofoam cup and put it in the oven. It's the heating process by these containers is typically microwave, but no, it actually shouldn't affect it at all. Yeah. Yes, so the question is about if we're offering alternatives, if people are getting concerned yet. The polystyrene has actually been banned in several states and a couple of countries outside of the US, but that's mostly due to its non-biodegradable qualities. It's not easily recyclable. So there are concerns, I'm sure, about the actual health effects. These studies have been going on for the past 15 years or so, and we still haven't found much. It's not exactly on the rise in terms of educating people on the effects or studying the effects. So I'd say it's kind of tapering off. Yeah. That's kind of beyond the scope of this paper that I wrote. Honestly, there's things, even things that aren't technically styrofoam, like milk containers that are cardboard, those are coated with polystyrene because otherwise the liquid would be able to basically absorb within the cardboard. So I did not study that, but it'd be interesting to see what the alternatives could be. Cool. Thanks.